short reads transcriptome assembly, and long reads error correction. So in short, a de Bruijn graph is the data representation at the heart of a lot of sequence analysis. Now let's see how do we convert raw sequencing data into a de Bruijn graph. Raw sequencing data has a bunch of reads, and a read is a string of bases over the DNA alphabet A, C, T, and G. And we use reads to extract k-mers, which is a substring of length k. In this example, you can see we extract k-mers of length 5 from the read. So the first k-mer is GGCCA, and you shift by one base, and then you get the next k-mer GCCAA, and so on. Now let's see how we use these k-mers to create this de Bruijn graph. In this talk, we're going to use this edge-centric definition of the de Bruijn graph. From that, I mean a k-mer acts as an edge in the de Bruijn graph, and it connects its two k-1 substrings. In this example, you can see the k-mer, which is a CAAAA, it's an edge, and it connects its two k-1 substrings that are CAAA on the left and AAAA on the right. When you have a bunch of reads, you extract k-mers out of it, and you create this de Bruijn graph by connecting all these edges. So in this graph, if you have read 1 and read 2, you extract edges that are CAAAA, AAAT, and so on, and you create this de Bruijn graph. However, there are many applications or analysis that needs a little more information in the de Bruijn graph. For example, the transcriptomic analysis, the topology-only de Bruijn graphs are not adequate for these analyses, and they need the abundance information of each k-mer in the underlying data set. Storing the extra information of the weights in a de Bruijn graph is an obligation, but it is an opportunity at the same time. And I'm going to talk to you and tell you about this opportunity later in the talk, that how we use this, the weight information, to actually correct all the approximation errors in an approximate representation of the weighted de Bruijn graph. A weighted de Bruijn graph looks similar to a standard de Bruijn graph. However, now all these edges have an abundance associated with them, which is the weight of that particular edge in the underlying data set. So in this example, the edge CAAAA appears twice in the couple of reads, so its abundance is 2, whereas other edges appear only once, so their abundance is only 1. Now let's see how do we measure the performance of the de Bruijn graph representations. De Bruijn graphs store only k-mers, so the space usage of the de Bruijn graph scales linearly with the number of distinct k-mers in the data set. For example, to represent a typical human genome in a weighted de Bruijn graph that has of the order of 1 billion distinct k-mers, the state-of-the-art solutions take something about 100 gigabytes of space. Whereas when you talk about transcriptomic analysis, for example, the soil metagenomes, where there are few million species involved, you take something about few terabytes of space. So like researchers in the past have been using beefy server machines to perform all this analysis on weighted de Bruijn graphs. Now let's see how do we represent a weighted de Bruijn graph and how we can optimize their space. To represent a weighted de Bruijn graph, all you need to do is that store a multiset of all these edges. For example, in this case, the graph on your right is a weighted de Bruijn graph where all the edges have weights associated with them. And on the left-hand side, you have a multiset, which is a multiset of all the edges, wherein each edge has a weight. For example, the edge TCCG has a weight of 2, and so on. In the past, people have worked to optimize the space usage of de Bruijn graphs by using an approximate membership query data structure to represent it. For example, Pell et al. First showed that you can use a Bloom's filter, which is an approximate membership query data structure, to represent a de Bruijn graph. They also showed that if the error rate of the Bloom's filter is less than 1%, then the overall structure of the de Bruijn graph is still intact. Pell et al. Followed up on the work and showed that the data or the elements inserted in the Bloom's filter are not independent, and they can exploit this, like the redundancy, to reduce the error rate of the data structure without increasing the space. Chiki et al. And Salikov et al. Showed that how you can convert this approximate representation of the de Bruijn graph into an exact one by using a small and exact auxiliary data structure. In debugger, we're going to show you that how we can use some of these tricks to actually extend them to the logical conclusions in a weighted de Bruijn graph. And we can build on top of it to give you a better guarantees on the structure of a de Bruijn graph when you have the weights associated with each edge. So to represent a multi-set compactly or approximately, what we use is a counting filter data structure. A counting filter data structure is the generic version of an AMQ data structure. In the counting filter data structure, you can associate weights with each and every element. And the errors are always one-sided. And similar to false positives in an AMQ data structure, you have the overcounts in a counting filter data structure. In our talk and in debugger, we are using a counting quotient filter, which is a recently introduced counting filter data structure, which gives you better guarantees compared to state-of-the-art other counting data structures. Now let's see. Pandey et al. First showed that what if you represent a weighted de Bruijn graph using a multi-set or like a counting filter data structure. When you represent a weighted de Bruijn graph in a multi-set data structure, you end up seeing two kinds of errors. The first kind of error is the topological errors that you see in the lower left, and these errors occur because of false positives in the approximation data structure, and they end up changing the structure of the graph. So in the graph, you can see the green nodes and the edges are coming from the actual data set underneath, but the red nodes and the edges are coming because of the topological errors, which is occurring because of the approximation data structure. There's also one kind of error, another kind of an error, which is the abundance error. And the abundance error happens when two elements or edges, in case of a weighted de Bruijn graph, that do exist in the input data set collide with each other and thereby increasing the weight of each one of them. In this case, the edge TCCG and AGCT, they both have an abundance of 2 in the underlying data set. But when you insert them in the approximate data structure, they collide with each other and increase the weight of both. So there are two kinds of errors, and now later on in my talk, I'm going to show you how we can use the redundancy in the weighted de Bruijn graphs to fix up all these approximation errors. In this paper, we're going to show you that debugger is an exact representation of the weighted de Bruijn graph. We have an algorithm that uses the counts in the approximate representation to fix up all the approximation errors iteratively. It corrects both kinds of errors, abundance errors and the topological errors. And at the same time, we do support queries for the arbitrary k-mers. The underlying data structure, it also supports deletions of k-mers, and that can be really useful for many downstream data analysis jobs. Compared to the state-of-the-art approximate representation of the weighted de Bruijn graph, debugger only takes 18 to 28% more space, and it has no empirical errors. Now let's see how debugger works. In debugger, we use a simple weighted de Bruijn graph invariant to fix up all these errors. And the invariant is very simple. It says that at any node in the weighted de Bruijn graph, the total incoming abundance is always equal to total outgoing abundance. For example, in this case, the node AAAA, there are 2 reads coming in. The blue bold paths are the paths of the reads in the de Bruijn graph. So there are 2 reads coming in and 2 reads going out. And the total abundance coming in is 2 because the edge coming in, that is CAAAA, has an abundance of 2. And there are 2 edges going out, both with an abundance 1. So this invariant holds for all the nodes in the weighted de Bruijn graph. However, there are some nodes for which to enforce this invariant, we need some extra information. For example, there could be some nodes where a read starts or ends. And in those kind of nodes, we need some little extra information. For example, in this case, there are 3 nodes, and the node in between, in the middle, is AAAA, where there are 2 reads that enter the node, but there's only 1 read that exits the node. So for each node in the weighted de Bruijn graph, we store or remember some extra information about that node. And that information is how many times that nodes appear at the start of any of the reads, or how many times that node appears at the end of any of the reads. And using this information, we can enforce this weighted de Bruijn graph invariant on all the nodes in the weighted de Bruijn graph and fix all these errors. Here is the representation of the weighted de Bruijn graph in debugger. You have a couple of reads, and you build the weighted de Bruijn graph on top of it. So you have 4 nodes in the graph, and you have the abundance for each and every edge. In data structures, we have three different data structures in the weighted de Bruijn graph in debugger. The data structure on the far left is the abundance data structure, which is an approximate representation data structure. And in debugger, we use a counting quotient filter for that approximation data structure. The other two data structures are exact data structures, and that store the information about the starts or ends of the reads for each and every node in the graph. These two data structures that are exact empirically are much more smaller compared to the abundance data structure because they only depends on the number of reads in your graph. Now, one thing important to note here is that right now the representation that you're seeing is an exact representation. However, since the data structure on the far left, that is the abundance data structure, is an approximate one, so you end up seeing some approximation errors. So here are some approximation errors which happen because of the underlying data structure approximation. So in this case, there are two errors. The first error is the introduction of a new edge, which is GGCTA, that is the edge on the bottom of the data structure. And because of that edge, you see two extra nodes in your graph on the top that are colored in red. And there's also one more error, which is an abundance error that happens because some other edge or the item that happens to be in the input data set collides with one other item in the input data set. So here, the actual weight for the edge AAAT is 1, as you can see here. But since there's an abundance error, the abundance of that edge becomes 2. So there are two kind of errors right now in this graph. And now we're going to see how we use the invariant to iteratively fix all these errors. The methodology is very simple. We pick one node, we try to enforce the invariant, and if there is only one way to change the abundance to fix that invariant, we do that. But if there are multiple ways, then we go to the nearby nodes, learn more information, come back, and then fix the abundance and enforce the invariant on that node. So let's see it one by one. First of all, we pick the node CCGT and try to enforce the invariant. Now, one important thing to notice here is that there is no edge coming into this node. So the incoming abundance at this node is 0. And as I already told you, the errors in the approximation data structure is always one-sided. That means the errors can only be overcounts. So whenever the data structure says the abundance of any edge is 0, that means it has to be correct because it can't be lower than 0. So since the abundance of all the incoming edges is 0, you know that the incoming abundance is 0. And since that node doesn't appear anywhere at the start or end of a read, you also know that to have this, the invariant enforced at this node, you make sure that the total abundance going out of this node has to be 0. So you fix this error by using this approximation, and you decrease the count of the edge CCGTA. Now it becomes 0. And since it was an error, you know that this edge doesn't exist in the input data set. Now let's pick another node. We pick this node, AAAA. Now you can see that total incoming abundance is 2, but the total outgoing abundance is 3. Now you know that you cannot enforce the invariant. To fix this node, you can do two things. One, you can decrement the abundance of the edge You can decrement the abundance of this edge to 1, and you can enforce this invariant. Or you can decrement the abundance of this edge as well, and you can still enforce the invariant. So there are two ways, and now we don't know which one to take. So we don't have enough information at this node. So what we do is that we go to nearby nodes, and we try to fix or enforce this invariant on those nodes and learn more information about the local graph. If we want to enforce this invariant on this node, it is same as the earlier node, CCGT, that there is no incoming abundance. And you know that this node appears twice at the start of reads, and the total outgoing abundance is 2. So you know that even without doing any change in the graph, the invariant still holds at this node. So you can safely say the abundance of the edge CAAAA is actually 2, and it is correct. Now you go to the next node, which is the neighboring node of the erroneous node AAAA, and you try to enforce the invariant again. Here it is again a similar thing, that the total outgoing abundance is 0, and the incoming abundance is 1. However, this node appears once at the end of a read. So again, you can say that without changing anything at this node, you can still enforce the invariant, and you can conclude that the abundance of the edge AAC is actually 1. Now you have learned enough information, and you can go back to the erroneous node, which you couldn't fix in the last iteration. Now you see that, you know that the abundance, so there are 3 edges neighboring that node AAA. And you know that out of those 3 edges, you know that the abundance of 2 of the edges is actually correct. So you can do, there's only one option to enforce the invariant, and that is by decrementing the weight of this edge. And you do that, and now you have a graph which has all the approximation errors removed. So this is how you use this simple weighted de Bruijn graph invariant iteratively on each and every node to fix up all these errors. The algorithm is a standard work queue algorithm. We bootstrap with a set of edges for which we know that the abundance is correct, and then we build on top of it. The proof is in the paper, and you can read it. It's a linear time algorithm. For the experiments, we use 4 data sets from the SRA. These are all transcriptomic data sets, and all of these data sets have more than 1 billion distinct k-mers. This is a bar chart in which the x-axis is the different data sets, and the y-axis is the space usage in terms of number of bits per k-mer. The blue bar is Squeaker, which is the state-of-the-art approximate representation of the weighted de Bruijn graph. The green bar is Squeaker exact, which is an exact representation of the weighted de Bruijn graph. And the blue bar, the yellow bar is debugger, which is the current system. You can see for all the data set, debugger takes almost half of the space as the exact representation, and it takes slightly more space compared to the approximate representation. But how about accuracy? So when we talk about accuracy, you can see the number of errors in Squeaker, which is an approximate representation, is of the order of few millions. But debugger has no errors. So Squeaker, which is an approximate representation, has at least 6 orders of magnitude more errors compared to debugger, and debugger only takes slightly more space compared to Squeaker. In short, number of errors in debugger is actually 0. In conclusion, I would like to say the abundance information is important for many data analysis, but the abundance information is also very useful for providing higher de Bruijn graph structural guarantees that are not available when you actually represent topology-only de Bruijn graphs using a Bloom filter. And we show that the abundance information can be used to remove effectively all the errors in an approximate weighted de Bruijn graph representation. The code is available online, and it is open source. Feel free to use it and send us queries. Thanks. I'll take questions.
We may have time for only one question.
Thanks for the talk, Prashant. Very interesting. When you make the correction to the count, is that done to the counting quotient filter, or is it done in an auxiliary exact data structure?
So right now, we maintain an auxiliary data structure for corrections. That's how we do it right now. But there's ways to adapt the quotient filter as well later on.
Okay, thank you.
No problem. Okay, thanks.
Let's take the speaker again. Our